Okay, so now this is chapter 6. So right after the test, we are going to go to a new chapter and a new topic, but still, this is related to chapter 5. So let's start with the first slide here. Um, so sort of like a review from chapter 5, the part that we need from chapter 5 for this chapter, I'm going through on this slide. Okay. Now in chapter 5, we talked about random variables. It is random variable is always a numerical quantity. It is a variable which has a number. And then so that takes different values like weight, height, GPA, all those are random variables. Now, the difference here is when you talk about random variables compared to variables in algebra, when you talk about random variables, we take chance into account. Okay, so in other words, it's not only the numerical value it takes, it's also the chance or the probability associated with each value. Okay, like for example, remember we talked about number of heads. If you were to toss a coin 3 times, and x had the values of possibly being equal to 0, 1, 2, or 3. Now, we did not stop at x being equal to 0, 1, 2, or 3. Those are the possible values that x can take. But we went further on and said that, okay, probability that x equals 0 is 1/8. Probability that x equals 1 is 3/8, and so forth. So that means we talked about the chance associated with each value. So that is what a random variable is about. It's a numerical quantity and the chance. So there are two pieces of information. Okay. Now also we talked about the fact that there are two types of random variables. Remember, in fact, there were times I abbreviated random variables as RV. Sorry. And then, so they were discrete random variables and continuous random variables. Discrete random variables means, you can, that's mostly count data. You can think of it that way. It is like values that have gaps in between. The possible values have gaps in between. But the continuous random variables, the values it can take are unbroken, like weight, birth weight, body temperature, for a given range, within a specified range, continuous random variables can take any value in that range. But discrete random variables, it's not the case. The values that the discrete random variable can take are distinct or discrete. They are not connected. Okay? All right. Now, in this chapter, which is chapter 6, what we are going to talk about is a specific discrete random variable. Okay, so but before we get into that, let me go through one more slide, sort of like a review from last chapter. Remember, we talked about this example where we had 4 patients, and then there was a treatment or an intervention with a 75% success. So if you apply this intervention on 4 patients, there are all these possibilities. No patient will be okay. Exactly 1 patient will have success. 2 patients will have success. 3 will have success. And it could be that all of them, okay, have success. So all these possible values are possible. Okay. So now if I define x to be the number of successes, see, now let's get used to these terms. So if you think about each single person here, or the patient, each person has 2 possibilities. Either this intervention could be a success for that patient or a failure. So there are 2 possibilities. So actually here you're sort of counting the number of successes, right? There could be 0 successes, 1 success, 2 successes, 3 successes, or 4 successes. Now, at the same time, there is a chance associated with each one of these because we are considering x to be a random variable. So the chance associated with each of these is given in here. In fact, we do not know still exactly how to calculate them. We will learn them. We will learn how to calculate. Now, this is that probability x equals little x In fact, I also introduce this other notation. So let me put that in here. Hmm, just I could say like that, right? Um, so let me make this small so that it will all be in one. Okay. Make it a little bit more small. Okay, so oops. Uh, just make all these small. Okay, all right then, and then oh, don't expect this to take this long. Okay, so now this little p of x, which we sort of, were introduced to in chapter 5, it is just notation again, just to make this a little bit simpler. This is little x, the possible values that the random variable big X can take. Okay, now this is actually nothing but PMF, the probability mass function, and we talk about PMF for discrete random variables. Okay, so that's good bit of notation and terminology here. So PMF we talk about for discrete random variables, and notationally it is either P within parentheses little x, or probability that big X equals little x. Okay, now with these values you just have to accept for right now, but we will learn how to calculate this, in fact, in this chapter. Okay, all right. So now again, remember, I said for discrete random variables, um, the specific values can be labeled. That's another way to figure out whether a particular random variable is discrete or not. This is like the first possible observation, this is a second possible value, this is a third, and so forth. You can label them, but if you think about birth weight, can you think of a way of labeling? No. What is the first possible weight? Even if you start with 6 pounds, what is the next possible? Is it 6.1? But no, there's always, weight measurements between 6 pounds and 6.1. So you cannot label. So such measurements are actually continuous. Okay. All right then. So let's start with chapter 6 proper from next slide. Now in chapter 6 we are talking about binomial probability distributions. Now binomial is a discrete random variable. Okay, is for is a discrete probability distribution. Okay. Um. Um. Okay. So let me put that within parentheses. Maybe I'll just write it like that. Now, why do I say it's a discrete probability distribution? Because the random variable associated with a binomial probability distribution is discrete. Okay, so let's see how we define it formally. Let's go to the next slide. Okay, so binomial random variables are discrete random variables. Okay, and we talked about discrete random variables in lesson 5, and also we reviewed in the previous slides. Now, then 6.1 in the textbook, you will be having an introduction. And then 6.2, we will be learning how to calculate binomial probabilities. 6.3, cumulative probabilities. Remember, we talked about cumulative. That is the probability up to a certain point. Okay, so these two sections are quite important. And then, um, this talks about probability probability calculators, how to calculate probabilities using software, And then also we will talk about expected value and the variance. And then of course we will be doing certain problems in the textbooks. Now in the slides yes, and we will, let's see, I may not go as far as this because it, the presentation will be too long, and then if that is the case, it's difficult for me to upload it. So perhaps, depending on how much time I take, I may not go as far as these two in this presentation. Okay, right. So at least up to this point, we will be going 6.4. Okay, all right then, let's go. Okay, so binomial in general is a family of discrete random variables. Family means, it varies from one particular value to the other. We will understand what is meant by a family in here. So now let's first of all understand what a binomial random variable is. Okay, it is actually coming out of a process. Okay, see, what's happening is, think in terms of tossing a coin 10 times. If you toss a coin 10 times, and if you count the number of heads, very similar to the example that we have been talking quite a bit, there of course we took n equal to 3. Let's think about 10 just to vary the n value, okay? So the number of possibilities for x will be varying from 0, 1, 2 up to 10. It can take any integer starting from 0 up to 10. Now that will be discrete, right? X equals 0, 1, 2 up to 10 is a discrete random variables. Now, so how do you get this? X equals number of heads is the number of successors, okay? Number of successors, right here, out of n independent Bernoulli trials. Now, what is meant by a Bernoulli trial is one single trial. In this particular example, one single toss is a Bernoulli trial. Now, what is the special property of a Bernoulli trial? It has only two possible outcomes, success or failure. So, tossing a coin is a Bernoulli trial. One single trial is if you just toss the coin once, okay? And then you will get heads and tails, and you can, label either one of these to be success, and then the other one will be failure. Of course, it is typical to label heads to be success. Okay, that's what everybody has been doing. Okay, now if you do that, now there is n, which is number of trials. Here you are tossing the coin 10 times, so that means n equals 10. And p, which is the probability of success of each trial. Think in here, if you were to toss the coin, what's the success of, getting a head? Here, success is heads. That's what we are labeling, we are labeling heads as success. So p would be 0.5. There's a 50% chance of getting success. Okay, so these are, you can call them, in fact, I can put a little note in here. N and P are called parameters of the binomial probability distribution. Okay, all right. So now see n and p. Oops, I need to make this lowercase. Now see, in here we used n equals 10. We tossed the coin only 10 times. But you can toss the coin 100 times. You can toss the coin 3 times as we did previously, right? So n is varying, but for a specific experiment it remains the same. Okay, for this particular experiment n will be 10. But for another day, you can take n to be 20. And also for another situation, p could be different. If you think about that patient's example, 4 patients, there p was 0.75. The success for the intervention was 0.75. So P also can vary, so can N. In that patient example, N was 4. Okay. So now, how is the family built now? Depending on N and P, as you keep on changing N and P, you get whole lot of binomial probability distributions or binomial discrete random variables. So you'll get a really big family of binomial discrete random variables with different N values and different P's. So that is why it is called a family. Okay, all right, because N and P vary. Okay. Alright, so let's go to the next one. Now keep in mind, whenever we talk about a binomial random variable, first thing that should come to your mind is what is n? How many times has the trial being repeated? Okay, and the trial should be Bernoulli. That means only two possible outcomes, success or failure. And then do you know the probability of success? Okay, so we need to, think of those two quantities, which are also called parameters, whenever we want to work with the binomial probability distribution or a binomial random variable. Okay, all right, let's go to an example in the next slide. The same example. See that the if you think of the patient's example, 4 patients example. Now that is and if you count the number of successes, now this x will be a binomial random variable. Okay, so x, which is the number of successes, is binomial. And the moment we know something is binomial, what should come to mind is what is n, what is p. N equals 4 because there were 4 patients involved, and p is 0.75 for each patient. Okay, if you think of all those patients are similar, each patient probability that the innovation will be successful is 75%. Okay, now notation wise, here's how you say, if you know that x is a binomial random variable, that means you are counting the number of successes, you will write it as b within parentheses n comma p. So here n and p for this example will be replaced by 4 and 0.75. Okay, now for the previous example, p was 0.5 and 0.5 and n was 10, right? Okay, so let's go to the next one. Now, so we know a description of a binomial random variable. So we know x. Next thing is, it being discrete, we need to know what the PMF is, probability mass function. Remember, little p value, probability that x is equal to little x. Now that is what we are going to talk about in the next slide. And here we will be using a formula. Okay. Now in the first case, remember when we did the number of heads 3 times, we could figure out this probability that x is equal to either 0, 1, 2, or 3 just intuitively, right? 1/8, 3/8, 3/8, and 1/8 for 0, 1, 2, 3. Now, when it gets complicated for a binomial random variable, we can use this formula. So probability that x equals little x. Now little x can be anything from 0 to n, anything meaning any integer. Notice here, there are gaps. You cannot have fractions for a binomial random variable. And then, so this little x varies from 0, 1, 2, all the way up to n. Okay. Now this again are some mathematical symbols. Now this is I don't know, some of you may be knowing this. It is available in some of the calculators. This is called the binomial coefficient. We will talk more about this in the next slide. And usually when you talk about that, this is how I say n choose x, like that. Okay, so n, sorry, this should be n. So n choose x. So that, see, in fact, this has another meaning, and because this is the quantity, this is a symbol of how many groups of x you can get out of n people. Okay, now in fact we will talk about that in a later slide. So that is why this verbal way of telling n choose x is meaningful. Okay, anyway, now and then you have p to the x. P is the probability of success, and this little x is the same as x. Now that can vary from 0, 1, 2 and so forth. Okay, now p is the probability of success. Now what is q? Q is probability of failure, which is 1 minus p. Okay, so if you have p equals 0.75, just like in the previous example, the intervention success was 0.75 probability, right? Then failure will be 0.25. It's pretty simple. Okay, so q and p are related. They add to 1. So if you know p, you can get q, and if you know q, you can get p. Okay, now and then of course you raise it to n minus x. We will be discussing how to apply this into numerical situations. Let's keep moving. Let's go to the next slide. Yeah, now to talk about the binomial coefficient. Okay, so this mathematically is equal to this. Now this symbol is n factorial. Okay, and then again in the next slide we will be talking about how to calculate. I think I skipped a slide here. Let's see. Yeah, all right here. Sorry. Okay, so now, here we are talking about the binomial coefficient, and then here's the symbol for it, and this is the formula. Now, this is the exclamation mark, and this is called the factorial function. It's really simple when you go to calculate it. The general formula is here. All you do is you start with this particular value, and then you take the product of everything by subtracting the first value by 1 and then by 2 and so forth all the way down to 1. So like for example 4 factorial will be you start with 4 times 3 times 2 times 1, and then you multiply them all together to get 24. Okay, now I'll just pause here just for you to glance at this a little bit. So that's how you get the factorial. And then now 1 factorial by definition will be 1, and also 0 factorial by definition will be 1. Okay. So for example, if you are to plug for n and x numerical values, 4 C2 will be 4 factorial, right? Divided by 2 factorial, and then n minus x will be 4 minus 2. We need to do the simplification within parentheses first. Do not take this exclamation inside, okay? You know the rules of arithmetic. You need to simplify within parentheses stuff first, right? So 4 minus 2 again will be another 2. And then you can spell it out. 4, 3, 2 times 1, and then cancel everything, and then you will get 6. Okay, so now what it is saying is 4 choose 2 is 6. Okay, and then in the binomial formula you can plug that in. Now also this has another meaning. I think in the next slide we'll talk about that. Let's see. Yeah, so now actually we calculated 4 choose to be equal to 6. Now what this means is there are 6 ways that you can choose 2 people or 2 items out of 4. So if I have 4 students in my class, and if I like to make pairs of students, I will have 6 different pairs of students. So that's what this means. So now that is why, when you talk verbally, you will say 4 choose 2. Okay, so the term choose makes sense because this gives you the number of ways that you can choose 2 people out of 4 or 2 items out of 4. In general, number of ways you can choose little x items out of little n. Okay, all right. Now for the binomial formula, you will of course have to plug the numbers in here. Okay. Now actually this is an applied stat course, a basic stat course. I don't think you will need to know how to plug this in. because you are going to use software or tables to calculate these binomial probabilities. But if you are a math major, or if you are interested in theoretical statistics, if you like to take more advanced stat classes, certainly this will be important. On the other hand, if you are interested only in the applied nature of statistics, you don't have to worry too much unless you like math. Okay. All right. Okay, so let's go next slide. So now, okay, see, here's a binomial calculation. Let's think about applying that formula into a particular example, the same example. Now, so again, so x is binomial with n equal to 4, p equal to 0.75. Then q will become 0.25. Remember, q is probability of failure. Okay. Now, say, how will you answer a question like this? What is the probability of observing 0 successes? That means in this particular example, you are applying that innovation for 4 people. What's the sad chance that nobody will be successful? Okay, so you need to find it out. Okay, so let's see how that works. What does that mean? Little x equals 0, right? No successors means little x equals 0. So you need to find probability that x equals 0, which is actually, if I am to use symbols in here, but I cannot put that in here, it is actually p within parenthesis 0, right? So actually I need to make this little p. Okay, and then p within parenthesis 0, and then you need to plug n was 4, here x is 0, then p was 0.75, x is 0, then q is 0.25, n was 4, x is 0. And then once you plug all the numbers in here, you get this. Apply the formula of 4 choose 0, you will have 4 factorial, 0 factorial, 4 minus 0 will give you 4 again, so 4 factorial. And then you will get these two. All you have to do is just simplify the exponent here. 4 minus 0 is 4. And then of course, look, 4 factorial here cancels very conveniently. And 0 factorial by definition was 1. So this whole thing reduces to 1. And now we know mathematically anything raised to 0 is 1. That is how we got this 1. And then if you use your calculator and then use the power button, you can get 0.25 raised to 4 to be this. Okay. And then once you multiply all that stuff, you will get 0.0039. So the chance that there will be no successes at all is 0.0039. It's sort of like about 0.39, about 0.4% chance there will be of no successes. It's not that high. So most probably, at least one person will end up having a successful intervention. Okay, in my opinion. Okay, so let's go to the next one. Okay, so likewise you can calculate x equals 1. What is 1? 1 means there's exactly one patient who was successful out of the 4. It matters, okay, how many you are choosing, how many are in the sample. So you plug the same way and then you get this answer. That means there is like 4.69% chance, right, that there will be one success, exactly one success. It seems as if the success is, the more successes, the chance for more successes is increasing because see, 0.75 for each trial is pretty high. 0.75 is pretty high, right? X equals 2, that means 2 successors is about 21%, 21.06. Okay, so you can go over this again, and then then likewise x equals 3, x equals 4, all successors, there's a 31% chance. Look, that's pretty good. And the highest chance is like 3 out of 4. Makes sense. 0.75 is like 3 out of 4, right? Okay, now all these we calculated are called exactly equal probabilities. See, probability that x is exactly equal. Now we need to think about the other type of probability, cumulative probability, which is also important. So next slide, in this slide we will be talking about that. Now cumulative distribution function the shorthand notation for that is CDF, and notationally it is x is less than or equal to little x. So actually for that particular example, we can calculate CDF. This is the PMF, right? And then, so we can see x varies from 0 through 4. So when you plug x equals 0 here, probability x is less than or equal to 0 is the same as x equals 0 because there's nothing else before 0. So this will be the same. X is less than or equal to 1 means x can be either 0 or 1. So you add these two, you get this. You can check it yourself. Once you add these two, you will get this. Okay. X is less than or equal to 2 would be, you need to add all these three up. Or you can add this with this, add this to get this. That's what I have shown in here. Okay. So likewise, you can keep on adding these numbers to get this. And then finally, you can notice the last possible value will have a cumulative distribution function of 1. Okay. Now, so that is how you find the CDF values. Okay. Okay. So the book also talks about this. Let's see. Yeah, in this one, so this is, I think we talked about this even in chapter 5. Cumulative probability is actually the left tail. Okay. Okay, so let's go to the next one. Yeah, so you can go over this. You know, it shows like in detail how you get each one of these. I mean, it's pretty simple. All you do is, you know, once you calculate x less than or equal to 1, you need to add these two to get x less than or equal to 2. You need to add 0, 1, and 2 probabilities together to get this. Like that, you know, keep on adding, and you know, and it's pretty clear that how you get that. Now, the next thing is how to find the expected value. I think I have little time. Let's go over this. Remember, we had a pretty heavy formula to find the mean summation x times px. Luckily for the binomial random variable, you don't have to go through all this. See, this is the formula, remember? This right hand side becomes n times p. It's really simple and intuitively it's so clear. Okay. So, you know, if you have 10 successors and if you have 10 tossers, right? And then p equals 0.5, think of getting heads. You will expect about five heads, right? So 10 times 0.5 is 5. Okay, so it's really intuitively so very agreeable, right? And then sigma squared, rather than use this entire formula, you can just say n times p times q. Really, really convenient. But remember, these two apply only for a binomial random variable, not for any discrete random variable. For any discrete random variable, you need to use these formulas like we did in chapter 5. Okay. All right. Then let's go. But remember, this is really neat for a binomial random variable. Okay. So here we can calculate mu to be 3. On the average, you will expect like 3 patients to be successful. If you have 4 patients, it's important. N is important. And sigma squared is 0.75. You can check the arithmetic when you have a little time. And then, okay, here's how you calculate binomial probabilities. Now, using Minitab. Now, if you are to use Minitab, you know, through Penn State, you can connect to web apps, okay, through this link. And then once you log in using your Penn State ID, you can get to Minitab. And then let me go, these are the commands to use. In fact, I have the screenshot here of Minitab. You will see something like this. This is a box that you will see. Now, if you want to find PMF, remember exactly equal probabilities. I will write it in here. Exactly equal probabilities. And then a CDF is cumulative, remember? So that means up to a point, or the okay, up to a point or the left tail, right? Now, if you want, using Minitab, if you want PMF, you need to go to the probability option, which is right on top here. You click on that. If you want the cumulative probability up to a point, you need to choose the cumulative option, which is the second one, okay? We don't need this right now, but pay attention to the two top options in there. And then you need to put in your number of trials in here, n, and then event probability is the same as success probability, okay? And then right here you click input constant, and then this will get activated or highlighted. Then you will put the little x you want. If you want to find the PMF for x equal to 1, you will have to put 1 for input constant. X equals 2, you have to put 2, and so forth. And then you click OK, and then you will get the answer right here. Okay? All right then. So remember, let me write it in here. Actually, number of trials, for number of trials you enter n, and event probability you need to enter little p, okay, little p. All right, so I think I made a mistake here. All right, so I mean, this is very convenient. If you just log into web apps at Penn State, you can access Minitab, and then you can use Minitab. Now the book also provides another software called stat table, and then it gives details in here. I'm really not, I mean, if you like, you can do this, use this as well, but it's a good idea to learn a more better used, like a more widely used software. Minitab would be one example. In fact, Excel, you can even use Excel to calculate binomial probabilities. I'll just mention that in here. You can also use Excel to calculate okay, since almost everybody has Excel, I think that's a good idea to get used to Excel, calculating statistical stuff using Excel as well. Okay, all right then. I think that's the end, but I think we need to do some word problems on this, and then I will certainly include some of them in the next presentation, or I will have some documents. Okay, all right then. Take care.